So, good afternoon, everybody. And now, the last lecture, as you know, we started with the topic of solid solutions, which we did a bit of it. And let's just, first 2-3 minutes, let us revise whatever we did in solid solutions in the previous class. So, solid solutions, as I described, they are basically, you can also call them as the extrinsic or the non-stoichiometric defect because they alter the stoichiometry of the material once you make the solid solution. And what exactly is a solid solution? It is a crystalline phase that has variable composition, and this is how it differs with the compound because your compound will have only single composition, but both of them are single crystalline phase. Okay. And of course, we talked about why at all we should study solid solutions and some examples. Then we also studied that solid solutions could be of two types. One is your simple solid solution, wherein you simply replace your host ion by the guest ion. And basically, because their charges are similar, so it is a simple replacement. And then we studied about the Hume-Rothery rules that govern the simple solid solution formation. Okay, then interstitial solid solution. Of course, the simple solid solution, first we talked about substitutional solid solution, and then we had interstitial, wherein your guest ion goes in and occupy the interstices in your host. Okay. Then we started what we call as the complex solid solution. Okay, when do we get complex solid solution? Now this complexity arises when your host ion and your guest ion, they do not have similar charge. And then we also discussed about what could be the two scenario. One is your host ion has got the charge higher than the guest ion, and the other one is the charge on the host ion is lesser than the guest ion, and what all could happen. And in this, we studied the first scenario wherein the charge on the guest ion is greater than host ion, in which we expect the formation of either the cation deficient solid solution or the anion excess solid solution. And for both the cases, we tried to sort out how to write the nominal formula when I'm assuming one of these mechanisms. Repeating it again for you, that whether a solid solution will form and what would be the mechanism. When I say mechanism means whether it would form by taking out, by making the vacancies that we call as anion deficient or cation deficient, or by putting in extra interstitial, which we call as cation excess or anion excess, that can be determined only experimentally. Of course, as I also mentioned in the last class, that your experience with a particular type of material can also help you predict and gauge what might happen. But to be very sure, these things can be studied only by experimentation. So we also tried to do a little more complicated example of what would happen when you will substitute niobium niobium oxide in Fe2O3. Okay. So I hope you understood it that day. If at all there is any doubt, you're free to mail me, and then we can discuss this again at the end of the class, that is on Monday, which would also be my last class with you. Okay. So, starting here, the last slide we did in the last class. Okay, so this is again another example of the case that we were already studying when your guest ion has got a charge more than your host ion. Okay, but I'm not going to repeat it because I explained it pretty well and in detail in last class. But I'll just go through it fast. If there is any problem, please write in the chat box. Okay. So as I said, whenever we are substituting, the condition that has to be satisfied is electroneutrality. So just for the ease of writing nominal formula, I can see that when I want to balance the charges, then 2 aluminium ion will be equal to 3 magnesium ion. Okay. So when we want to write cation deficient solid solution, so what is happening is if I want to replace magnesium by aluminium, 3 magnesium, 2 aluminium going inside the lattice will have to take out 3 magnesium. Out of these 3, 2 will be occupied by 2 aluminium that are going inside, and one site would be vacant, which we can write as Mg. If 2x of the aluminium goes in, then how much magnesium do we lose? 3x. So how much magnesium is remaining in the lattice? 1 minus 3x. Then 3x magnesium goes out, 2 of it is occupied, and then x is a vacant. So how many vacancy? Vx. Okay. That is how we write the nominal formula when we get cation deficient solid solution upon substitution of Al3 plus in MgO. On the other hand, if the mechanism of solid solution formation was anion excess, because that also could be one of the mechanism of electroneutrality in this case, then of course we do not disturb cation at all. X aluminium goes in, 1 minus X magnesium is left, and how much oxygen do we increase? See, the formula was Al2O3, that is AlO 1.5, and magnesium oxide. So every aluminium that goes inside MgO takes along with it 0.5 oxygen extra. So X aluminium will take X by 2 oxygen extra, and that is how the formula is 1 plus X by 2. Okay. This I have repeated many times that the mechanism of solid solution formation has to be determined experimentally. Now, coming to the second scenario, which is when the ion that you are doping, that is your guest ion, has got lesser charge than the host ion. Then what would happen? Okay, so let us take the example of substituting calcium in ZrO2. Zirconium has the charge of +4 and calcium ion goes in as +2 ion. Okay. Now the guest is taking lesser positive charge. That means either you will have to compensate it by introducing extra positive charge, which means cation excess, or you will have to take out some negative charge, which means anion deficient. Okay. So we can write, when we want to write the anion deficient solid solution, I write Zr and I write O2. And of course, I'm putting in calcium. Okay. So since I'm talking of anion deficient, I'm not going to touch the cationic lattice. So X calcium goes in, zirconium left is 1 minus X. So what is happening? What will happen to anion? It is anion deficient. So how much anion should I take out? Okay, so you had ZrO2 and you have CaO. So for every Ca that goes in ZrO2, you actually have to reduce one oxygen, because every Zr has 2 oxygen, every Ca has 1 oxygen. So it is less by every Ca 1 oxygen for each Ca, X oxygen for each Ca. That is the formula for anion deficient calcium doped zirconia. Okay. So when I want to write cation excess, okay, no problem. Then how do we go about it? I have ZrO2. Now I am assuming that my charge balance mechanism involves extra calcium. Okay. So now Zr4 plus is equal to 2Ca2 plus, right? 4 plus and 2 calcium will make 4 plus. In that case, if I substitute 2x of calcium, then my X zirconium goes. Okay. Because every calcium will remove half zirconium in terms of electroneutrality. So 2 calcium means you'll have to knock off 1 zirconium. 2x calcium means x zirconium has to be knocked off, and this is the nominal formula for the cation excess solid solution when we substitute calcium into zirconia. Calcium based stabilized zirconia, yttria stabilized zirconia, they are all technically very important material. They exhibit a wide variety of properties because of the fact that they're good catalysts, they're good oxide ion conductor. Okay, so anion deficient zirconia. Now in this you see, as I told you in the last class, when you want to design the ionic conductors, you have to see two things. A, you should have charge carriers. B, you should have pathways for those charge carriers to move. Then only the conduction can happen, right? So here, anion deficient zirconia has got oxygen vacancies. That is why they are oxide ion conductors. Okay. So this is an example of when your charge on the guest is less than the charge on the host. Double substitution. Till now we only talked about the cation substitution, but can the double substitution happen? Of course it can happen. Substitution at both cationic and anionic side, though they are not that common as we discussed in the last class. The substitution in anionic sites are rather lesser, fewer as compared to cationic substitution example. Why? Because there are very few number of pairs of anions that have got similar bonding and coordination requirement. But one such easy example is NaCl and AgBr. If you mix, they form solid solution in the entire range. So silver occupies the sodium site and the charges are similar. So simple solid solution, no fuss at all. Similarly, chloride and bromide ions, similar charge. So NaCl and AgBr, they form solid solution throughout the range. Similarly, Si3N4 and Al2O3. You substitute, they also form solid solution in the entire range. You substitute Al3 plus for Si4 plus, so you have reduced one positive charge. But when you replaced oxide ion for the nitride ion, you similarly have reduced negative charge by one. So the charge balance is taken care of and we get 100% solid solution of this formula. X aluminium goes in, silicon left is 1 minus X. For every aluminium that goes in, corresponding oxygen is also going on inside the lattice, and this is a nominal formula, and these kind of compounds are also in short called sialons, and they're very important refractory materials. What are refractory materials? The materials that have application at high temperature. Okay. So just two example of how the double substitution, that is substitution at both cationic and anionic side, can happen. Okay, now you have formed the solid solution, but how would you study them? Okay, you need to study them as well. When you are doing solid state chemistry, your bread and butter is X-ray diffraction. Whenever there is anything related to crystal structure, you can study that system by diffraction. That could be X-ray diffraction, electron diffraction, neutron diffraction. Out of them, of course, in terms of availability, X-ray diffraction is most available to most of us. And that is why this is the first technique that we resort to when we have to do the structural study. So what can X-ray diffraction tell you when you're studying solid solution? A, whether it has formed or not. Because if it is not formed, or if you have already reached the solubility limit, that is only 30% A only could have gone into your B. Whatever it is, it will show you from the XRD pattern, you can analyze whether the solid solution has formed and what are the solubilities. Also, if your solid solution is formed, it will also have its structure. It will also have its lattice parameter. So those lattice parameters, the cell parameters, can be determined from X-ray diffraction studies. What is another technique that you can use other than diffraction? See, when you are creating vacancies or you're putting in excess, you're basically changing the density of the material, right? That is the most direct impact of making solid solution, creating vacancies or putting in interstitial, that the density would change. So this is also one very important parameter that can help you to study the solid solution that you are playing with. So solid solution formation will affect the density, and this can be measured by Archimedes principle. Using the concept of Archimedes principle, the density kits are available in many of the labs that can be used to measure that. So what you do is basically, okay, we'll come to that in next slide. So as is obvious, as you can expect, that the presence of vacancies will lead to decrease in density, and the presence of interstitial will cause the increase in density, and this will give us an idea of what is the formation mechanism, whether you're working with cation excess and ion excess, or you're working with cation deficient and ion deficient, of course, depending on the relative charges of host and guest ion. The other properties that you can employ to study the solid solution are the thermal properties. Okay, and that can be done using DTA and DSC. Why? Because once you have formed solid solution, your composition has changed. That will affect the melting point. So you can determine the melting point of the material. If it has changed, then your solid solution. Also, for example, presence of as small as 0.2% carbon, 0.2 atom percent carbon in iron can reduce the melting point by more than 150 degree. That is, goes down from 910 to 723 degree. So your thermal techniques can also be employed to study the solid solutions. Okay. Now, when we talk of studying solid solution by X-ray diffraction, there is a concept that we talk about, which is called Vegard's law. What is Vegard's law? Vegard's law states that if you are forming the solid solution between two components A and B, then the lattice parameter of the solid solution will be the linear function of the composition. That is, what it wants to say is, okay, that is, if suppose you are forming solid solution between Syria and YSZ. I have taken this example because this is what I have done myself in my like 20 years back during my PhD. So this is what I could actually observe. So if you're plotting, you're making the solid solution between Syria and YSZ. Okay, so what I observed was both of them are fluoride type and both of them are miscible in the entire range, starting from 10% of YZ in Syria to 20 to 30 to 40 and hence going on. And then what I did was I recorded the XRD for all the 11 compositions and then calculated their cell parameter from XRD pattern and plotted it. So with respect to the composition, I could have chosen mole percent YZ also, that would have been same. When I plot the lattice parameter, because it is cubic, so A is equal to B is equal to C. So I plotted A because cerium ion is bigger than, now YSZ is zirconia stabilized yttria. So average of Y3 plus ZR4 plus whatever composition I took. Obviously, when you are putting a bigger ion, here I'm plotting with respect to Syria. In a smaller ion, you are expecting that the lattice parameter would increase. And this is what I observe. Increase in the lattice parameter. If I had plotted it with mole percent of YSZ, then I would have observed this. Okay. So what it essentially says here is Vegard's law. Vegard's law says that lattice parameter of the solid solution formed between two solids A and B is the linear function of the composition. That is, you would observe a linear function, like a linear plot, okay? But having said that, this is a oversimplification. Many a times Vegard's law fail. Why does it fail? Because what it is assuming is, what did I tell you when I showed you that slide? that you are substituting a smaller ball by a bigger ball. So obviously you would expect that there would be increase in the average size. But the problem is, this is exactly the problem. What we are assuming is that your host and the guest atom, they are hard spheres, they are incompressible, and your lattice parameter would depend only on the relative ionic or atomic radii of host and guest. But we know that this is not the case. There are other interactions that are happening between the ions. So if your AA and BB interactions, they are greater than the interactions AB, which will happen in the solid solution when you mix them, you will observe a positive deviation from Vegard's law. You will observe a non-linearity, and that non-linearity also will have a positive deviation because A and B are not happy being close to each other as compared to what they were in their own parent side. But if your AA and BB interaction are less than AB interaction, what you will observe is the negative deviation from Vegard's law. Okay, so this is just an example for you to show what happens when we get solid solution and how to observe it from the plot. So this is a Syria YSZ system. This is the XRD pattern of Syria, fluoride type Syria. Okay, this is the XRD pattern of YSZ. Okay, if you remember, I don't know whether I told you or not, but you must be knowing that XRD pattern is a fingerprinting of the material. So here it is obvious, as you can see, XRD pattern of Syria and YSZ, they look alike. There are 1, 2, 3, 4. All the peaks, whatever are happening in Syria, are also being shown in YSZ. Okay, then how do I call it fingerprint? Because they are similar. If I'm given the XRD pattern, would I be able to point out whether it is Syria or YSZ? Of course, Dr. Kanu Barik will tell you these things in more detail, but the patterns are qualitatively similar. If I was able to zoom it for you, or if you can really make out, you will see that even though the pattern of Syria and YSZ are similar, the peaks of YSZ are shifted to slightly higher angle. Like this position would be at higher angle than this position. And this comes from your Bragg's law, which is going to tell you. Okay, coming back to what I am teaching you here. So when, let's say, of course, I made 10 compositions in between Syria and YSZ, but here I'm showing XRD pattern of the one that contains 50-50% of YSZ and Syria. So what do we observe is A, the lattice, the XRD pattern is similar to what I've got for Syria and YSZ. That means, and there are no extra peaks, okay? That means a complete miscibility has been obtained in Syria and YSZ in this particular nominal composition when I mixed 50-50 mole percent of these two, Syria and YSZ. And also, if I am able to zoom in for that, zoom in for you, you will be able to see that these positions are actually between the ones for Syria and YSZ, and that is the reason you observe this linearity in Vegard's law. On the other hand, when I tried to make similar phase relation between Thoria and YSZ, there was absolutely no miscibility from both ends, despite the fact that even Thoria also crystallizes in fluoride type like Syria and YSZ. So Thoria and YSZ did not show any miscibility. Of course, we'll talk about the reasons, not here because that is not in purview of the class. I only want to show you how you can study whether your solid solution is forming with the help of XRD. So when you look at this composition, where I have taken 50-50% of Thoria and YSZ, you see that there is one set of peaks that corresponds to Thoria, and there is another set of peaks that corresponds to YSZ. That means both Thoria and YSZ, they want to remain their own identity. They do not want to mix up. And this is how we use XRD for studying whether our solid solution is formed or not. And how do we use density measurement for the same? Very simple. If you know you have the density kit with you in the lab, you can determine the density of all the solid solutions that you have formed. And theoretically, you assume that it was forming a cation excess and an anion vacant solid solution, and assuming both, you determine the theoretical density and plot them. And then you determine the experimental density and you see which line it closely matches, and that would be giving you the hint of, or an indication of, or rather the confirmation, if you are able to get good values, that what is the solid solution mechanism being followed in your system. For example, in calcium zirconia system, assuming that it form, now it can form an ion vacant or cation excess. So you assume that an anion vacant solid solution is formed. You know the nominal formula, okay? So you can calculate what would be the theoretical density. So calculate all the theoretical density for 5 mole percent, 10, 15, whatever composition you have taken, and then plot it. Similarly, assume cation excess and then plot it. And these black dots are the experimentally measured values, and they match closely with the hypothesis that I have got anion vacant solid solution mechanism, and hence this is how it shows that this particular solid solution adopts the anion vacant mode of mechanism of solid solution formation. Similarly, this graph shows what happens when CaF2 is doped in YF3, and here it could be shown that anion excess was the mechanism that was being adopted. Okay, so that gives you an idea of the mechanism that is being followed. Okay, so what did we learn in this particular lecture? What are exactly the solid solution? We know that these are the non-stoichiometric defects that we create deliberately, and hence they are called extrinsic defect. What are the different types of solid solution? Substitutional, interstitial. What are complex solid solution? We also call them aliovalent. So what is the term? What are the term? Isovalent and aliovalent. Isovalent means when your guest and host have got similar valency, and aliovalent means when they've got different valencies. And we studied what are the consequences on solid solution formation, and also the techniques, how can we study the solid solution formation. So here we'll take a break for 2 minutes before we jump on to our next topic of phase transitions. If you have any doubt, please write in the chat box. Okay. All right. So to start with the next topic, and that is the second last topic in your general materials core chemistry course of this module of your AMC course, is phase transitions. Okay. So as the name suggests, basically what is phase transition? Your phase transition is nothing but if a material has the propensity to exist in more than one polymorphs, more than one crystalline form, then transformation from one to another is called the phase transition. That is, I'll repeat again, change of one crystalline form of the material to another and in response to either temperature or pressure. Okay. So I'll repeat again. If a material has the propensity to exist in more than one polymorph, then change from one crystalline form to another in response to change in temperature or pressure is called phase transition. Of course, most of the time, sometimes the phase also changes in response to composition. We just studied solid solution, okay? For example, I started with A and I keep on substituting B in it. Suppose there occurs AB. Now AB itself undergoes, let's say, phase transformation from phase 1 to phase 2. Then this is called the phase change in response to the composition. That also is called phase transition. But conventionally, the phase transition is actually denoted when the crystalline form of the material changes under the effect of temperature or pressure. Okay. So what are polymorphs? I have just mentioned that there are two or more different crystalline form of the same material. For example, if I talk of SiO2 silica, there are four crystalline form of silica: quartz, cristobalite, tridymite, stishovite. Okay. Interesting part is all of them consist of the basic unit silica. But how these silica units are arranged, that defines that particular polymer. Similarly, we talked about barium titanate quite a few times in last few lectures. Barium titanate can exist in tetragonal, which we know is a ferroelectric material. And it can also exist in cubic form. So cubic and tetragonal are the two polymorphs of barium titanate. So how I can classify the phase transformation? Of course, based upon the thermodynamics that is characteristic of that particular phase transition. And therein we talk about what is the thermodynamic order of phase transition. We'll come to that a little later. Of course, the phase transformation can also be classified as what is the mechanism being followed. And based upon the mechanism of phase transition, there are two categories of phase transition. One is called the reconstructive phase transition and the other one is called the displacive phase transition. What is the difference between these two? So reconstructive phase transition, as the name suggests, is the phase transition that occurs by breaking and then rejoining of the bonds. Okay. That is, when you want to go from phase 1 to phase 2, you have to break many bonds and reform newer bonds. Breaking of old bonds, formation of newer bonds. That is why reconstruct are called the reconstructive phase transition, because you are reconstructing the second phase. Because they involve breaking and reformation, they are slow. Because they involve breaking of bond, they involve high activation energy. And also, because you have broken the bond and then you have reformed a new bond, it is not essential that the two polymorphs will have any symmetry relationship between them. For example, one biggest example and the most simplest example of reconstructive phase transition is phase transformation from graphite to diamond at high pressure and temperature. How are they different? See, both of them are made up of carbon, right? But your graphite has got sp2 carbon and it is a layered structure. All of us know about that. Whereas your diamond, it is your three-dimensional structure of sp3 carbon. Each carbon is linked to four other carbons, okay? Same carbon linked in a different manner, two different polymorphs, and you for converting one polymorph to other, that is diamond to graphite or graphite to diamond, you have to do a lot of bond breaking and bond formation. and this requires high pressure and temperature, and that is why this is an example of reconstructive phase transition. Similarly, silica has got four polymorphs I showed you earlier. Transition between those polymorphs, that is quartz to cristobalite, cristobalite to tridymite, is also an example of reconstructive phase transition. Second category, displacive phase transition. What does it mean? Again, as the word indicates, in displacive phase transition, the phase transition happens when atoms are simply displaced with respect to one another by smaller distances. Okay, the bonds are not broken, and because the bonds are not broken, this does not involve a lot of activation energy. And because the bonds are not broken, these reactions are relatively faster as compared to reconstructive phase transition. And because it is only the displacement of atom with respect to one another, there is a definite symmetry relationship between the two polymorphs that are linked by a displacive phase transition. All right. I hope it is very clear. I'm not going to repeat it because these are simple concepts. Example is low or high temperature phase transition in all the polymorphs of silica. What does it mean is, as I told you, silica has got three polymorphs: quartz, tridymite, cristobalite. Their alpha form transforms to beta quartz, beta tridymite, beta cristobalite. Okay. Now these three are linked by reconstructive phase transition, but each one of them, okay, like quartz has got a low quartz and a high quartz, alpha quartz and a beta quartz. Similarly, tridymite has got a low tridymite and a high tridymite. So alpha and beta are linked by displacive phase transition, but quartz and tridymite are linked by reconstructive phase transition. Similarly, alpha tridymite and beta tridymite are linked by displacive phase transition, but this and this are related by reconstructive phase transition. Okay, so this is what is the difference. This example clearly brings out the difference between the reconstructive and displacive phase transition. Pictorially, just to show you, suppose you have this structure, okay? Now this structure is got, if you look at it, this is basically one atom linked to three other atoms. Now it can be linked in this way and it can be transformed to these three. But transformation from A to any one of B, C or D is a reconstructive phase transition because you'll have to break and reform. But from B to C or from C to D, it is only displacive phase transition. They are only slightly shifted with respect to each other. Okay. Again, just to visualize what is the difference between these two kind of phase transition. Okay. Just give you another interesting example of displacive phase transition. Rock salt structure, I'm not saying rock salt type of structure transforms to cesium chloride type of structure by a displacive phase transition. And how does that happen? Okay, so let us now concentrate what is a rock salt structure. The rock salt structure is phase center lattice of one ion. Okay, wherein octahedral interstices, rock salt structure, yes. Okay, wherein your octahedral interstices like your H center and the body center are occupied by the second ion. Just repeating it again. Let's say I'm talking about NaCl only. Na occupies your corners and face center position, and Cl occupies your body center position and the edge center position. Okay. And now how is it a displacive phase transition? How simply by moving the bond can I bring it to CaCl structure? What is the CaCl structure? Okay. It is a primitive lattice, so chloride at the center and all the cesium at the corners. Now let us see how just by sorry, displacing, you can convert rock salt into CaCl. Just concentrate on your rock salt structure and concentrate only on the atoms that I have marked here, only on the lattice point that I've marked here. Okay, I'm concentrating on these 8 Na ion and the chlorine at the center. Okay, now what you do is you hold lattice point 1 marked here and lattice point A by your two fingers and then try to push them inside. Bring them in and then concentrate on it. What will happen is your corner atom A, your face center atom 3, face center atom 4, and face center atom 7, they will form corners of this cube this way. Okay, 8, 3, 4, 7, now they form a particular face. Similarly, your corner atom 1, face center atom 5, atom 6, which is at the face at the back. Okay, and then atom 2, which is at the face center position of this bottom face, they form the lower face of the new cube. And your chlorine, which was at the center, remains at the center. But in this process, what has happened is your NaCl kind of structure has converted to cesium chloride type of structure. Right? What has happened is the coordination number, which was 6 for chlorine, if you concentrate of on the chlorine in rock salt structure, it had 6 sodium around it, which are lying at the center of 6 faces. But that has now converted to coordination number 8 because the sodium that was lying at position 8 and sodium that was lying at position 1 has also come in its first coordination sphere, raising the coordination number from 6 to 8. Okay, so this is an example of displacive phase transition. Rock salt type of structure at high pressure or low temperature can go to your cesium chloride type of structure. Okay, another classification will not do this. What is the effect of pressure and temperature of phase transition? Okay, so these are some of the general guidelines that will tell you how do pressure and temperature they affect the phase transition. Okay, so what happens is, let's talk about the very general and logical scenario. What happens when you increase the temperature? What kind of phases would be stabilized at higher temperature? The phases, because now you're increasing the temperature, they will expand. So high temperature phases have more open structure and more symmetrical structure also, because now they are trying to occupy a bigger space. So they will tend to be more symmetric. And at the higher temperature, your the structure will be more open. It will be more symmetric. It will have lower coordination number. Also, if there is a chance of ordering and disordering, your high temperature structure would be more disordered. So what are the 4 things that we talked about? The high temperature phases would be more open, more symmetric, ions will have lower coordination number and they'll be more disordered. And mind you, I want you to pay a very close attention to the fact that I've mentioned more disordered and more symmetric. That means you have to understand that symmetry and ordering are two different things, which is of course very clear, but many a times I have seen that students, they tend to confuse between these terms. Okay. Now, opposite, high increase in temperature means you're now tending to expand the things. Opposite will happen in pressure. Pressure means you're trying to compress it. So when you're trying to put pressure, what will happen? High pressure phases, you're trying to bring everything closer. They'll be more dense. Okay. And because you're trying to make everything come closer, the atoms or ions will have higher coordination number. Also, they will be less symmetric because they'll try to fit in as many ions they can, and there are chances of them losing symmetry in that particular scenario. So they'll be less symmetric, but they'll be more ordered. So high pressure, the effect of pressure is totally opposite the effect of temperature on the phase transition. High pressure phases will be more dense, they'll be less symmetric, they'll be more ordered, and the atoms and ions will have higher coordination number. Okay. For example, for AB type of compound, the compound which has 1:1 stoichiometry, if I have a cesium chloride type of structure, mind you, cesium chloride will not go into NaCl. Cesium chloride type of primitive lattice with increase in temperature has the propensity to go to rock salt type of structure. The rock salt type of structure will further increase in temperature, goes to zinc sulfide type of structure. Okay. And the reverse will happen with increase in pressure. If I look at the coordination number, we just said that increase in temperature will lead to decrease in coordination number. Coordination number 8 with increase in temperature goes to coordination number 6. This with increase in temperature goes to coordination number 4. And the reverse happens with increase in pressure. So effect of pressure and effect of temperature on phase transitions are generally antagonistic. They work in opposite directions. All right. Now, there is a very important and very interesting category of phase transition that I would like to talk about, which is called the order disorder phase transition. Now, what do I mean by that? What is ordering and disorder? Okay, a phase is called, and we have talked about it in some different contexts. If you remember the fluoride pyrochloride that we talked about. So pyrochloride was an ordered phase of fluoride. All right. We'll go into the in a simplistic manner. If you have a crystalline phase AB, where your A and B have got distinct site occupancies. What does it mean is that if I point at a particular lattice site, I should be able to say that this site is occupied by A or this site is occupied by B. Then that structure is called an ordered structure. However, for the same composition AB, if it is a disordered phase, what will happen is my each lattice site, I will not be able to say with the surety whether that is occupied by A or B. I would say that it is the probability of that site being occupied by A is 50%. Okay. Or the probability of that site being occupied by B is also equal. That means that A and B are randomized over the entire structure. And that is what I call as the disordered phase. Similarly, suppose my composition was A to B. In this case, ordering can happen in any way, but in whatever way it happens, I would be able to say with certainty that A is present on this side and B is present on this side. But when it is a disordered structure, I would say that the probability of B occupying that particular site is 1/3 and A occupying that particular site is 2/3. So what does it say? That when A and B, a disordered phase is the one, when A and B are distributed in the random way, occupying with the probability, and that probability depends upon the nominal composition, any atomic site of the lattice. For example, if I'm talking of 50A, 50B, lattice AB, let's say your blue squares are A and your green squares are B, this is a random structure or the disordered phase. This is an ordered phase. Okay. So I hope you have understood what I want to say here. And as we discussed in previous slide, ordered phase, if there is a possibility of order disorder also does not happen in all the compounds. But if there is a possibility of an order disorder phase transition, then low temperature phase is generally the ordered phase. Increases because increasing the temperature will cause the randomness, which will lead to the disordered phase. Okay. Whereas as the temperature decreases, A and B, they prefer only certain specific site. There will be two distinguished sublattices. Okay. So now another important term that emerges when we talk about superstructure. What is a superstructure? So the ordered structure of a particular composition, okay, it is called the superstructure of the disordered structure. That is the long range ordered structure that is generated after ordering of A and B. And I will try to show you an example. How does this affect your XRD pattern? Okay. Now an example to show you ordering and disordering. This is your beta brass, the alloy of copper and zinc. Okay. What happens is at low temperature, it occurs as a primitive lattice. This is your low temperature site. That means where your, let's say your zinc is present in the body center and copper are present on the corners. Now this is a primitive lattice because I cannot call it a body center, because you remember I said we can call it body center only when the atom present at the center of the cube is similar to the atom that is present at the corner. But here, because this is the ordered phase and zinc is everywhere occupying that body center, this is a primitive lattice. With a lot of certainty, I can say that copper is present at the corner, zinc is present at the body center. But as you increase the temperature, what happens is copper and zinc, they swap the position. The randomization increase and you result with this unit cell. Now, what does it mean? This means that the probability of finding copper or the probability of finding zinc at any of the lattice site is 50-50. Consequence is that your atom at the lattice site at the center is similar to the lattice sites at the corner. Okay. So now what has happened that your primitive lattice has converted to the body centered lattice. Okay. On increasing the temperature. Okay. So also this also shows one more thing which we talked about in the last slide. Increasing the temperature increases the symmetry of the phase. Okay. So it goes from primitive to body center. The symmetry increases. Another example. There you had Cu and zinc in 1:1 ratio. Let's talk about Cu3Au. Okay. Now Cu3Au at low temperature, this is how it exists. So what you have is at corners you have all Au and all at the face centers you have Cu. This is the primitive lattice. But when you increase the temperature, they all randomize. The average atom is now 1/4 of Au and 3/4 of Cu. It converts to FCC. The primitive lattice converts to FCC lattice. So what has happened is an order-disorder phase transition. Okay. So similar is the example shown by cobalt platinum. So what are the conditions for ordering? If I mix any two elements A and B, will they order? No. See, for ordering, the affinity of A towards A should be less than the affinity of A towards B. That is, then only they would want to be with each other, right? So for ordering, the atoms should be dissimilar in terms of their sizes, in terms of their charges. For example, you get brass, which is copper zinc, you get bronze, which is copper tin, but silver gold alloy you ordering, you will never hear. Why? Because silver and gold are similar in their properties. They would never order. Howsoever low temperature you take. I mean, at least whatever I have read about it. Okay. So, present for ordering to occur, there has to be more affinity between AB than AA and BB. But what are the effects of ordering? How would you know? See, you had a powder, you heated it or cooled it, and you recorded, and you simply heated it and cooled it. How would you know whether the ordering disordering has happened? When you get ordering, the symmetry decreases. Okay. And if I don't know, Dr. Kanu Barik will take XRD for you. And some of you might have studied also. when you have higher symmetry, that is BCC lattice, FCC lattice, or side-centered lattice, the number of peaks in their XRD pattern are lesser than the primitive lattice. That is, lesser symmetry means more peaks in the XRD pattern. So, and higher symmetry means lesser number of peaks in the XRD pattern because there are certain systematic absences. So, the extra peaks that you observe because of lowering of symmetry, those extra peaks are called superstructure peak, and appearance of superstructure peak is a clear indication of occurrence of ordering or the superstructure in the material. So XRD can tell you if the ordering is happening. Similarly, when you have an ordered structure provides better pathway for the charges to conduct. Okay, more ordered, less scattering, better mobility, better pathways, there is an increase in ionic conductivity. The ordered phases are also more malleable and ductile, and because they are ordered, they have better packing and higher density. Okay, so these are some of the physical properties in conjunction with XRD that you can measure to see whether you have observed order disorder transition or not. Okay, now I just brought out one example from studies in our group only to show you what are the superstructure peaks. Okay, this is GD2ZR207. It forms pyrochlore structure, but it has very weak ordering. Because if you remember, I told you that depends on RA by RB, but just forget that. Just remember that it has weak ordering. And as I'm substituting neodymium in it, the RA by RB is increasing, which means that it should now become a better ordered pyrochlore. Now you see that the main peaks are all similar, right? Because the basic lattice is fluoride, but pyrochlore is a superstructure of fluoride. And how is it manifested? That these big peaks, they belong to fluoride. And these small peaks that you observe here, if you are able to see this, they correspond to the pyrochlore type of structure. And as I am substituting ND, I'm going in this direction. I'm increasing RA by RB. My ordering is becoming better. And please try to concentrate on the intensity of the superstructure peaks now. Okay? Now these peaks are increasing in intensity. So these are the peaks that show me that the ordering in my material, the degree of order in my material is increasing with increase in neodymium content. Okay. There's another phase transition I would like to talk to you about before winding up, which is called martensitic phase transition. Okay. It's a very, very interesting class of phase transition. Now, these are the phase transition which are diffusion-less process. No diffusion happens. The diffusionless process and the material changes the crystal structure without any of the atoms to change position by more than one lattice spacing. Many a times it is only a fraction of the lattice spacing, and this is observed in many metallic and non-metallic systems. Okay, that means the relative position of the atoms and ions in the parent phase and the product phase, or in phase 1 and phase 2, remains similar, but the change in the crystal structure occurs. These happen without any movement of the diffusion of the atoms or ions. And if I would want to tell it to you, basically, if you can remember what is dominoes effect, like they arrange playing cards one over the other. If you just slightly move one card, each will follow simultaneously, and all the playing cards, they ultimately go to the ground. So this is called the dominoes effect. It is something like that. And martensitic phase transition can, now what is the example? What is the proof that they can, they are diffusionless processes? Because some of the martensitic phase transition have been known to occur at low temperature where the diffusion is absolutely not possible. Okay, diffusion of the atoms or ion requires some energy, some temperature. The martensitic phase transition can be brought about by temperature, as well as the mechanical forces in the cooling process. And the extent, and like other phase transition, they happen sharply at TC from phase 1 to phase 2. But in case of martensitic, there is a hysteresis that occurs over a broad range of temperature. Okay, so there is a hysteresis. It happens on the range of temperature and the extent of transition, like how much of phase 1 is converted to phase 2, that will depend upon the temperature and not on time. Diffusion are either not happening, they're much less than interatomic spacing. Atoms retain their relative relationship, and also, as I told you, that it happens as a dominoes effect. So they move in a very choreographed manner. It is also called the military transformation. And how they are different from your displacive phase transition that we talked about earlier, they are super fast. They're very fast. In many cases, they actually equate the speed of the sound in that particular material. Okay. So it is very difficult to stop them. Okay. So for one of the, now these phase transition have actually been named after the phase transition that happens in steel. Now steel is alpha iron with carbon in the interstices. It occurs in the phase that we call as austenite. Okay. Austenite is an FCC structure where iron has got carbon in the interstices. If you take austenite and quench it to lower temperature, it will form martensite. So this particular phase transition, martensitic, has got its name from austenite to martensite phase transition. Martensite is body centered and it is so fast that the carbon that was in the interstices of austenite, it still remains in the interstices of martensite. So it happens as if it is a single phase transformation. Okay, single component phase transition. Now this martensite, austenite, you cool, it goes to martensite. The martensite, if you start heating it, it will go to austenite, but now that transformation to austenite will happen at a temperature higher than what it was in the reverse direction. That is, you observe the hysteresis. For example, monoclinic zirconia to tetragonal zirconia is also a martensitic phase transition. Now this goes to tetragonal zirconia at about 1150 degrees C. But if you take the reverse transformation, if you start cooling it, then tetragonal to monoclinic will start only below 950. This is called the hysteresis. Okay. Now this simply shows austenite to martensite. Your austenite is face centered. Martensite, it becomes tetragonal and it becomes face centered tetragonal now. This just shows how the phase transition happened. Okay. These are the blocks of austenite phase. When the phase transition happens, it suddenly happens so that this block has become martensite. These blocks are still austenite. Okay. And they will also eventually convert to martensite, though very fast. But because it happens in a sequential manner, so that is why what happens is, because they happen in a sequential manner, they can be they happen over a range of temperature. So the extent of the transition depends upon the temperature. All right. So as here also you can see that the relative position of A1 and A2, B1 and B2 are still similar. So the relative position of the atoms do not change in two phases. It is a diffusion less phase transition. Okay. Now this is the last part of the lecture. Okay, I'll just take a minute's break and then we'll see. We saw how to classify the phase transition in terms of the mechanism, which was displacive and reconstructive. And now we'll see how to classify the phase transition in terms of the thermodynamic parameters, first order, second order, and so on. So we'll take a 2 minutes break and then we'll come back. Okay, thermodynamic classification of phase transition. You would have heard about the first order phase transition, the second order phase transition. So what does it mean? So before starting all this, I will try to explain one term to you that I would be using in next 10 minutes. What do I say when I say that the thermodynamic quantity is continuous? Continuous means, let's say I'm talking about the reaction at equilibrium. So at equilibrium, delta G is 0. All right. So delta G is 0 means, let's say my phase transition was happening from phase 1 to phase 2. And delta G at phase transition temperature is 0. Okay. So which means that G2 is equal to G1. Okay. Now because at phase transition temperature, the free energy of phase 1 is equal to free energy of phase 2, resulting in the fact that delta G is 0. So we say that G free energy is continuous at equilibrium. So continuity means that that particular thermodynamic parameter does not change at phase transition. This is a term that I wanted to make a little clear before I talk about other things. Okay, so the thermodynamic classification of phase transition is also called as Ehrenfest classification scheme. It says that order of the transition is the order of lowest differential of G, which shows discontinuity. I'll repeat again. What is the order of transition? It is the order of the lowest differential of free energy that shows discontinuity. For example, okay, now by this definition, what would be the first order phase transition? First order phase transition will be the first differential of G with respect to temperature and pressure should show discontinuity. Then we call that phase transition as first order phase transition, which means now what is the first differential of free energy with respect to temperature? From a thermodynamics, we at constant pressure, we know that it is minus S, and the differential of free energy with respect to pressure at constant temperature is P. Now, when we say that for the first order phase transition, the first differential of G with respect to temperature and pressure are discontinuous, means delta S is not equal to 0 or S2 is not equal to S1. That is at phase transition temperature, entropy of the second phase and entropy of the first phase are not equal. Free energy will definitely be 0 because it is continuous. Delta G has to be 0. Similarly, V2 is not equal to V1 and delta V is 0, not equal to 0. What does it mean? If I don't go into the technical term, it means that there has to be a volume change accompanying your phase transition. It's as simple as that. Okay. So repeating it again, first order phase transition means there is a discontinuity in first derivative of G with respect to temperature and pressure. Okay. This sign is not minus. This implies that at phase transition temperature, S2 is not equal to S1. V2 also should not be equal to V1. And by corollary, because your delta S is delta H upon T, so delta H will also not be equal to 0. That is, your enthalpies of the two phases would be different. So the fact that your enthalpies are unequal, you can use ETA to measure your first order phase transition. Okay. And the different volumes can be measured by dilatometry or high temperature XRD. So if you record XRD, and let's say from room temperature to 1200 in your high temperature machine, and your phase transition is supposed to happen at 850, you will observe a distinctive change in cell parameter at phase transition. If you are doing it by dilatometry, there will be a distinctive change in volume with respect at the phase transition temperature. Okay. By the same extension, what are the second order phase transition? there will be a discontinuity in the second derivative of free energy. But now the first derivatives will be constant, will be continuous. Continuous means there will be no change in volume, there will be no change in entropy and enthalpy. What will change? What is the second derivative? Del 2g by del t square is minus Cp by t. Del 2g by del p square is minus V beta. And del 2g by del p del t is V alpha. What are these factors? This you know is heat capacity. This is compressibility. And this is thermal expansion coefficient. Now, if you try to concentrate on these terms, compressibility, thermal expansion coefficient as well as heat capacity are very small quantity as compared to your volume and this thing. They are not small quantity. The changes in these values are even smaller. Okay, sorry, we are measuring these quantities. So the fact that these are very small quantities, when you try to measure Cp or thermal expansion coefficient, it becomes relatively difficult. So it is relatively difficult to detect second order transition because the quantities are very small. Okay. So in other words, if I talk of in a very physical sense, what does it mean? That first order phase transition are more visualizable as compared to second order phase transition, which happen silently. So heat capacity, this is difficult to measure. This you can measure. Normally, second order phase transition are measured by calorimetry because this is the easiest quantity to be measured for the second order phase transition. Okay. Now, just to explain you a more thermodynamic sense of it. If you don't know, ideally those of you who have studied thermodynamics should know. This is how the free energy temperature graph looks like for any material. Okay, just remember this thing. Now, for the first order phase transition, let's say I'm going from phase 1 to phase 2. All right. And I also know that delta G is 0. So remember that G2 has to be equal to G1 at phase transition temperature. Right? So how can I draw my G by T curve? This is G, this is T. Okay. Suppose this is my curve for phase 1. How can I draw the curve for phase 2? Every phase has to have a GT curve, right? Now I have to make sure, let's say this is TC, the phase transition temperature. I'm sorry for the drawing. Now at TC, your G has to be continuous. That is, the free energy has to be same for both phase 1 and phase 2. Also, above TC, phase 2 has to be stable, and below TC, phase 1 has to be stable. So can I draw the GT curve of phase 2 like this? See, it satisfies all the criteria. At TC, G of 1 is equal to G of 2. Above TC, the GT of phase 2 is lower, so phase 2 is stable. Below TC, the GT of phase 1 is lower, so 1 is stable. So can I draw it like that? This is how you represent the GT curve of the phase transformation, like this. Okay. How can you represent the volume? Volume is discontinuous, and the higher temperature phase will have higher volume. So this is V1, and at phase transition, it is discontinuous. So delta V is not equal to 0. As I can see, there is a jump in volume. This is V2. Similarly for entropy and similarly for enthalpy. So this is what I want to show you here. Okay. For the second order phase transition, now the story is a little different. I know I can draw my GT curve like this. Okay. Now I have to draw the GT curve for phase 2, and the conditions are delta G is 0. Okay. Now delta S is also 0 because the first derivative is 0. Now what is delta S? Delta S is del G by del delta T. What is this? This is nothing but the slope of the curve, slope of this GT curve. Okay. So this implies that at Tc phase transition temperature, the slope of my two graphs cannot be different for phase 1 and phase 2. Now that is a difficult thing to draw. This I can draw like this. Just look at this figure. At Tc, the slopes are similar. But what does it mean is that below Tc and above Tc, at both the places, my phase 2 is stable. Now, if phase 2 is stable in the entire temperature range, then why would the phase transition happen? So obviously this is wrong. Okay. But can it happen this way? It can happen this way, but in this case, you see that the GT curve of phase 2 is rather distorted. Okay, normally the GT curve do not happen this way. So this is also ignored. That means what is it that I can actually now get is something. If I want to draw the GT curve for a second order phase transition, what I can do is I can draw like this. Okay, so there has to be only a single GT curve. This region represents, this is TC. This region represents phase 1. This represents phase 2. What does it actually mean? This means that any second order phase transition is actually a transition wherein below TC, that process, that phase transition process, whatever mechanism was there, it has got over. That is, the phase 1 do not really exist below TC. Okay. So that is the difference between phase 1, first order phase transition and second order phase transition. Now for your ease, I will draw both of them and let us try to compare. Okay. This is my second order and this is first order. This is for phase 1, this is for phase 2, this is TC. Okay. Now, what is the implication of these two graphs? This shows that if your phase transition is first order, if at all, okay, then let's say I am above TC, I try to cool it, I reach TC. Okay, ideally my phase 2 should now convert to phase 1, which it will, because below TC phase 1 is stable. But by some means, if I am able to quench my reaction, let's say I have it at 500 or let's say 1000, from 1000 I dropped it immediately to liquid nitrogen such that it did not get the time to rearrange. There is a possibility that phase 2 might exist at temperature below TC. And that is called supercooled phase 2. What is the example of such a supercooled mixture? Supercooled material? Your glass. Glasses are supercooled material. Okay. Because of the fact that there is an existence of GT curve of phase 2 at all the temperature, there is still a possibility of obtaining phase 2 at temperature lower than TC if I am able to arrest this phase transition. Similarly, there is a possibility of obtaining phase 1 at temperature higher than TC because the GT curve exists. Though this is difficult, getting the supercooled phases are much easier as compared to obtaining the superheated phases. But when I am talking of second order phase transition, since above TC, the phase 1 does not exist at all. Okay. So there is still a possibility of getting a supercooled phase 2, but the possibility of obtaining a superheated phase 1 is absolutely not there. So this is a physical meaning of phase transition, first order and second order. Okay. So that was just to explain it to you, because there is no point in studying something if I'm not able to understand what is the underlying meaning of whatever I am saying. Just the last concept. What is a metastable phase? We've talked about the stable phases. So if you have the energy diagram of a material, we know that whatever material we have that lies in the, whether it is a chemical reaction or the energy landscape of a material, our material lies in the global energy minimum. But my energy landscape could have some local minima, which are not the least energy, but still they lie in some kind of a valley. So the materials that have got energy corresponding to these points are called metastable points. If you perturb them, they will eventually go back in this deeper valley and convert to a stable phase. But many a times, there are some material which, if you are able to obtain their metastable phase and you do not perturb them, they can actually remain in that metastable state. And how do we get the metastable phase? They are kinetically stable state, because thermodynamically, obviously, this is not stable. Thermodynamically, this is your stable situation. So metastable phases are obtained if you are able to control your synthesis route by kinetic methods. Okay, so that is what an example is. Your diamond is a metastable phase at room temperature. Okay, so it is stable. If the entire diamond had gone to graphite, which is a stable phase, now you think of no diamond jewelry would have existed ever. Okay, so that is what I wanted to tell you. And just another thing, if you remember this curve that I was talking about, phase 1 at temperature below Tc and phase 2 at temperature above Tc are the metastable phases, because they are not supposed to exist. All right. So this is what it is. So what we did is we studied what are phase transition. We studied what are the classification based on mechanism and classification based on thermodynamics. We also talked a little about what is Martin-Sittig phase transformation and what are the effect of pressure and temperature on phase transition. With this, we wind up this class. Any questions? Just in next 1 minute you can ask, else you can mail me, and you can also ask me the questions in the next class, or whenever you have any doubt, you're most welcome to contact. Anthony, the displacer phase transitions are mostly reversible. Martin-Sittig are definitely reversible. See, wherever you have lower activation energy or zero activation energy, those phase transitions would be reversible. Okay, so no more questions. Then I'll meet you on Monday at 4 o'clock, and that would be the last class of this particular module. Thank you so much and good day.